Thank you, and it's a real pleasure for me to open the day and to see that some of you could wake up this morning. First, I would like to thank the scientific committee, Corinne and Jean-Christophe for giving me this very nice opportunity to present some of our research. And today I'm going to present our work on light conversion at nanostructured electrodes. So first, I would like to mention that most of the results that are going to be presented here actually are the results of the LICON project, which is a nationally founded project by ANR, which involves 4 teams. So we are 2 teams in Rennes, so my institute, where we are doing most of the photoelectrode preparation and photoelectrochemical characterization. 1 team also in Rennes, Institut Photon, where they are providing their expertise in terms of spectroscopy and optical setup. 1 team also at the University of Bordeaux, who is expert in electrochemiluminescence, and 1 team in Marseille, the CINAM, where they are helping with semiconductor preparation and characterization. So today I will present you an unconventional way that we can use to convert light, which involves an electrode. So this, I think you won't be so surprised, that is immersed into an electrolyte. Okay. So we are going to irradiate this electrode with an optical input of a specific wavelength, so lambda x for excitation. We are going to apply a little bit of electrical input too, and this will lead to an optical output at a different wavelength, which is called here lambda m. So this concept is based on 2 very different aspects of electrochemistry, which are semiconductor photoelectrochemistry on the left here, and electrochemiluminescence, which is known also as ECL. And so I will very briefly describe both of these aspects in a single slide. And I will start with semiconductor photoelectrochemistry. So when we do semiconductor electrochemistry, of course, we are using a semiconductor working electrode, which is immersed into a liquid electrolyte which contains 1 or several redox species, so in this case, A- A redox couple. And most of the time we are working in condition where our electrode is in depletion, which means that we have the formation of a depletion region here, and we have a band bending. Okay, and because of this condition, the charge transfer at the interface is not possible. So you see here that the electrons from this species cannot go into the conduction band because of this condition here. So in the dark, the oxidation is not possible in this case. However, under illumination, so if you irradiate this semiconductor with, and this is very important, with an optical energy which has a higher energy than the band gap of the semiconductor, we are going to generate electron-hole pairs. And the photogenerated minority carriers, in this case here holes, are going to be able to transfer through the interface and to oxidize our redox species. So in this case, under illumination, actually here, we have an electrochemical activity which is triggered by illuminations. And so what I would like you to remember is that in semiconductor photoelectrochemistry, the electrode is a light absorber. Now I will describe very briefly ECL. So ECL is a very different electrochemical concept, which is used typically in the dark on conventional electrodes such as glassy carbon. And so in ECL, we are using electrolyte which comprise 1 luminophore. This is very important because this is the molecule that is going to produce the light. And most of the time also a co-reactant. Here this is tripropylamine. So here you have the composition of the mainly used, let's say, ECL electrolyte, which comprises ruthenium trisbipyridyl as the luminophore and tripropylamine as the co-reactant. So how this work? Briefly, so if we apply a positive potential to our glassy carbon electrode here, we are going to oxidize simultaneously the luminophore and the co-reactant. These 2 oxidized species are going to react together, and this will lead to the generation of the luminophore excited state, which will produce light at a very specific wavelength, and in this case about 630 nanometers. And what is important here is that in ECL, the electrode is a light emitter. So now we are going to combine these two phenomena together. So on the left, you see we have, if we use a semiconductor, then our electrode is going to be a light absorber. And if we use the ECL electrolyte, we are going also to have a light emission. And so since 2019, we are working on that, and we refer to this phenomenon as photo-induced ECL, PECL. So before I present experimental results, just one slide to just remind some very basics of photoluminescence. So luminescence process can be divided in two categories, okay? Stock type luminescence, this is typically fluorescence is a stock type process, and in stock type process, high energy wavelength, high energy light is converted into light of lower energy. So you can see it here on this Wikipedia picture. So here we have a green laser, which is actually irradiating two test tubes. In the first test tube, there is a fluorescent probe. So the green light here is converted into a light of a lower energy, so red lights. And in the second test tube, we have an opposite phenomenon, which is an anti-stock phenomenon. So this is the second type of luminescence. And this is what occurs for upconverting particles, which are able to convert light of a low energy into light of a higher energy. And one thing that is very interesting with PECL is that actually we can do both types of phenomenon using a PECL. So I will present you in these two examples to illustrate these two types of conversion mechanism, and I will start with anti-stock PECL. Okay, so for this story, most of the results were obtained by two PhD students, Yiran in Rennes and Julie in Bordeaux. Maybe you already met her because she was on stage yesterday during the show. And she's going to, more importantly, she's going to present a talk this morning on ECL. And so in this system, we used an electrolyte which comprises actually exactly the same ingredients that I presented to you before in the two last slides, so ruthenium trisbupyridyl and tripropylamine. Here you can see the spectral characteristic of this electrolyte, so it absorbs below 600 nanometer. Our luminophore emits at 632 nanometer. So now that we have selected the electrolyte, we need to select a semiconductor to be used as a working electrode, and we wanted to use with silicon. The problem with silicon is that it's highly unstable in aqueous electrolyte, and especially when we use it as an anode. So we needed to find a way to protect it, and for that we coated it with a tunnel silicon oxide layer and different metal coating. So we tested different ones. Here you can see the characterization data for iridium. Here AFM, we see, so the gray data are before deposition of the iridium thin film, and the red data is after the deposition of the iridium thin film. So on the spectroscopy data, you can see here the band gap position of silicon. This is very important because, as I mentioned, if we want to use this material as a photoelectrode, we have to excite it with an energy which is higher than 1.1 eV, which is its band gap. So we have to work in this region, okay? And this is why then we chose an excitation wavelength of 850 nanometer, which is in the near IR, which is invisible by the human eye, and which is enough spaced from actually the emission and the electrolyte absorption. So we are sure that there won't be any fluorescence process occurring during our experiments. Here you can see a scheme of our system. So we have our silicon photoanode with the two thin protection layer. We are going to use a front side illumination, which means that we are going to irradiate through the electrolyte and the protection layers. This protection layer is very thin, so the near IR light can actually generate photo electron hole pairs. The photo-generated hole are going to be collected at the metal thin film and are going to trigger the ECL reaction, which will lead to the formation of visible light. So here, if this works, we should have an anti-stock PECL process where near-infrared light, so low energy light, is converted into a visible light with a higher energy. This is a scheme of the photoelectrochemical setup that we are using, which is based on the classical photoelectrochemical cell. We illuminate with the IR LED. We use a dichroic mirror, and we use a spectrometer to record simultaneously the photoelectrochemical response and the emission. These are the typical data that we obtain. So here you see on the top cyclic voltammograms obtained in the dark or under near IR illumination for two different metal protection layers. So in red, iridium, in blue, you see platinum. And in the bottom, you see this is the same potential x-axis. We see actually the luminescence intensity, which was recorded simultaneously. So here we see that in the dark, there is no electrochemistry occurring, so no current, no light emission. This is because this junction is depleted and rectifies the current. However, under illumination with the near IR light, we have photocurrent generation and associated with PECL emission. And for those who have already worked on ECL, you can see that for this system, the onset potential for the ECL generation is very low. And this is a peculiarity of PECL. I don't have the time to discuss this in detail, but if you want to have more details, I would be very happy to discuss that with you later. So now, how long can this work actually? So here you can see some stability tests which are actually done galvanostatically. So we apply a constant photocurrent density. The red data is the data obtained for iridium thin film. The blue data is the data obtained for platinum thin film. The lines are the potential of this working electrode, and the disks are the normalized PECL intensity. So we see that for a platinum protection layer, it works for a couple of hours. So we have a stable PECL emission, but we see that the potential of the electrode is drastically increasing over time, which means that actually the resistance, interfacial resistance is increasing. The electrode is actually not stable. But for iridium, it works very nicely. As you can see here, the potential of the electrode is stable for more than 35 hours, and the PECL emission can last for a very, very long time. So this shows that by applying the proper protection layer, then we are able actually to make this PECL system last for a very long time, which was very important for us. So all these results were obtained with homogeneous illumination of the surface, and so all the immersed photoanode surface was emitting light. We can also do localized PECL, and there is two ways to do that. So I show you here the first way to do that is actually just to use a very collimated near IR beam. So if we are using a laser, actually we can generate a tiny spot of visible light. So here you can see a photo of our setup. We have the different elements. Okay, this red thing is the ECL electrolyte here. The green discs represent the active surface of our anode. The IR laser, which is invisible, and this is 840 nanometer, comes from the right to the left. And you see actually the tiny red spot we see here is actually the PECL process. So here we have red illumination due to this upconversion process. So I have a video, and in this video you can see that actually when we move the laser on the surface, we can the PECL spot is also moving. So this shows that we can select precisely the place on the electrode where we want this upconversion process to occur. Another way to do a localized PECL is actually to use patterned, to illuminate the whole photoelectrode area homogeneously with the IR light, but instead of using a metal full film, we just use a metal pattern. So the photo-generated hole will be, because silicon oxide is an insulator, they will be collected at the metal thin film, and the reaction should occur at that place. And this is what happens. You see on this very nice microscopy picture that was obtained by Julie in Bordeaux. You see that indeed it works. So here we have several thickness, several widths of iridium bands from about 10 micrometer to 50 micrometer. And you see here that indeed this pattern is revealed. So this shows that PECL is occurring locally. So this ends the first part of my talk, where we discussed anti-stock PECL, and now I will present a couple of results on stock-type PECL. And this work has been done by former PhD students, so Ying in Bordeaux and Iba in Rennes. And so they work with this other electrolyte, which contains a luminol analog, which is called L012, in alkaline medium. And here you can see the spectral data for this electrolyte. So we see here that this electrolyte absorbs, so the luminophore absorbs below 450 approximately. And it emits, so the luminescence occurs with a maximum at about 500 nanometers. So what about now the photoanodes? So we are not working anymore with silicon, so we wanted to use a semiconductor with a broader band gap. So we used bismuth vanadate, which is an N-type material which is widely used for water splitting. You see that we deposited our bismuth vanadate layer on transparent conductive oxide, okay, FTO-coated silicon oxide. You see that this semiconductor has a characteristic very yellow color here. And here is now the band gap of bismuth vanadate, which is much lower wavelengths than the silicon. So here, if you remember, then if we want to do PECL, then we have to excite this semiconductor in this region. So instead of using IR light, then now we are going to use UV light. And you see the characteristic of the excitation we used. So when we use this UV light as an excitation source, we are generating holes in bismuth vanadate, and this is what we want to do. But at the same time, as you can see, we are also going to excite our luminophore. So this luminophore is going also to fluoresce, which was not the case previously. So here we are working in backside illumination configuration. So we illuminate through the glass slide, the conducting substrate that we use for depositing the bismuth vanadate. Because this electrode is pseudo-transparent, a part of the photons are going to reach the electrolyte, and LO12 is going to luminesce. And this is what happens where at open circuit condition. But when we apply the potential, PECL is going to occur simultaneously, and then we'll have fluorescence plus PECL, and this actually will lead to amplification of the luminescent signal. And so here we have a stock type PECL system where UV light, so high energy optical input, is converted into an input of a lower energy. Here you see cyclic voltammogram for this system, so bismuth vanadate in the ECL electrolyte. In the dark we have no current. Under UV illumination we have photocurrent. If we apply a potential to this electrode of 0 volt versus silver chloride, these are the spectral characteristics, we obtain the purple spectrum here. So the red spectrum was obtained in open circuit conditions. So we see the fluorescence of our luminophore, but when we apply this potential, you see that indeed intensity is increased. So we are actually, it's a way to control the luminescence intensity. So we studied different parameters and showed that actually we can control the amplification using the potential we apply at the electrode, the power input of the LED, and this system was stable for a couple of hours. So I will now conclude. So I presented to you PECL, which is a general concept that can be used for tunable light conversion. The very important features of PECL that cannot be obtained with ECL is that it allows for localized ECL generation using focused optic, for instance, and it considerably decreases the ECL onset potential. We have improved stability. When we started working in this field, the stability was for about 15 minutes to more than a day, so we are very happy about that. We think that there are potential applications in IR detection, biosensing, remote wireless ECL, multiple analysis on single electrode, and also for elucidating mechanism at photoelectrode for water splitting, for instance. And the current challenge we are facing is improving the spatial resolution and to improve the photovoltage of our system. Last but not least, I would like to thank all these people, especially the key people here. So Yeran, Julie, who has actually made the Licorne logo, and Professor Sojic in Bordeaux, and all the institution for fundings. And I thank you very much for your attention.